Welcome. Welcome, you just joined the club. Since we last saw you, I think our last marine evening was in November. I want to say a big warm welcome to Kari, our colleague who's back after 4 months. They pupped a little baby shark called Vickers. So she just came back like a week ago, so it's really great to have her back. And we've been incredibly busy. It seems super busy. It felt like it didn't stop over December. We've had wonderful sightings. We've had our 3 dolphin species that begin in the bay, our bottlenose, our common dolphins, and we had our endangered humpback dolphins, incredible sightings of them. We even had a dusky dolphin, and we were so excited. All of us working in the offices, we wanted to get out and to go see them. Our sharks, our bronze whaler sharks, been absolutely beautiful. They love the warmer water as well. And then our whales have just been incredible. It's always strange to us when we hear people say, oh no, the whales are only here during whale season. What is that? It's all year round. We've had the most spectacular humpback whale sightings today. He just kept on jumping. So we've always got our residential brood as well, and then of course our visiting southern white whales. But never say to people, oh, there's no more sharks, because the sightings of the great white sharks are slow or low. We've got bronze whalers, we've got 7 gills, we've got sharks, and we have got whales. Wilfred always jokes about it. He says only when Sandra, who's our head biologist for whales side, and only when she asks the mist to roll into the bay, that's the only days that we can't see the whales. Otherwise, we usually can see our beautiful, beautiful whales. We've had so many penguin rescues. We've been extremely busy during the fires as well. Other birds, such as the beautiful spotted eagle owl that we're still looking after. It was caught. He was like completely stuck in a fence. He's still at the African Penguin and Seabird Sanctuary. Quite a few penguin rescues that we got, but we have done quite a few penguin releases as well. So you can read about these releases on our blog, www.dict.org, the blog. Please go have a look there. Also our social media for Marine Dynamic Shark and Whale Tours, the African Penguin and Seabird Sanctuary, and the Dyer Conservation Trust. Because we need you to follow these stories and we need your support. Otherwise, we can't continue doing what we're doing. Even though it's only the end of February, we've had Zalea, our head of marketing. She was in India for 2 weeks. She did up to 55 meetings per day, seeing agents, seeing people to come to South Africa. It was a hectic 2 weeks. She just got back. She's now on her way to Berlin, also for an international travel market. Claudia is flying to Sao Paulo. She's going to be there for 2 weeks. Sancha's not here tonight because she's up at the garden route doing marketing. Wilfred will be going to the UK in June, and we've got so many more markets that we're planning on doing. Really trying to get tourists to be part of our non-consumptive ecotourism and to come and experience this marine life and also in return help us to better protect them. So we believe at Marine Dynamics it's incredibly important to do research about these animals, to have scientists that we work along, because the more we know about them, the better we can protect them. So tonight's speaker, she also joined our team in the beginning of January, is Dr. Loraine Shuttleworth. 2 weeks ago she was just Loraine, and now she's Dr. Shuttleworth. She just got her doctorate in ecology from the University of Pretoria, and she's going to talk more about her research that she's been doing for the past 5 years about southern right whales, and it's absolutely fascinating. Now, what Loraine can also do as a scientist, apart from being absolutely gorgeous and lovely, and it's so great to have her as a colleague, is she can do the thing that not all scientists can do, science communication. Those of you who've been here before for a marine evening would know that sometimes there's a scientist speaking, you go like, what are you saying? But Loraine can really explain things. So I sit across her from the table in the mornings when we're working or during the day, and I would ask her a question and she can give me a scientific answer, but I can understand what she's saying. Except for the one day, the first week that she started working here, and she went out to go do a necropsy, which is a dissection of a dead animal. It's like what do you call it if you do to a human? Autopsy. Anyway, but this is the animal version called a necropsy. And she gets back, and according to me, they were doing a necropsy on an octopus. And I say to her, how did it go? And she's like, yeah, it's a bit stinky, but it went well. It was still fresh. Good, good. Now, me from a BA communication, drama, media, talking to the scientists, And I said, because I know if you do an octopus, you need to get the mouth, you can learn a lot of things from the mouth. I said to her, did you get the mouth? And she like looks at me and she's like, no, he was quite young, so didn't get that, but he was definitely still suckling on the mom. And I'm like, damn, I missed that. And she looks at me and she can see my confusion and she says, you know they're mammals, right? And I'm like, now I don't know if I should say to her, I really didn't know an octopus is a mammal, or am I just going to play it cool and go, yeah, of course. And I said, an octopus is a mammal. She's like, no, I'm talking about a dolphin. So, but I really appreciate her answering my questions, although they were the stupidest questions, because in my mind I had this picture of the octopus and the babies drinking from it. So, thanks Loraine, it's great to have you here. There's going to be many stupid questions, and thank you for making science accessible to us and to translate it. So please give a warm welcome to Dr. Loraine Shuttleworth. Thank you.
Right, hi everyone. Thank you so much, Christine, for that introduction. So it is super exciting for me to be here. I think the first and actually only marine evening that I've attended was to come watch my supervisor speak. And when I was here, I found out that they had this position for the head of research, and it obviously made me super excited, and I applied. And now I'm super privileged to be part of this team and to be presenting tonight. So it's really special to be here. I'm going to try my very best, as Christine said, to explain everything as easily as possible, but sometimes I do forget that I've been so obsessed with this for the past how many years, and I think that some things are really easy to understand and they seem like common knowledge to me. So if there is anything that you didn't quite get, if I skipped over it or just nerded out far too much, please do ask questions at the end. Anyway, so this is basically an overview of my PhD. So we're going to start with southern right whales that are a capital breeding species. And that means that they migrate from their offshore summer foraging grounds, which are high latitude, so close to Antarctica, where they feed for about 6 months of the year. They then migrate to coastal areas like the coast over here, where they then come to give birth to their calves and to nurse their youngs. And while they're here, they don't feed at all, which is really interesting. So their migration cycles are very closely linked to their reproductive cycles because they need to very carefully balance the time that they spend at the feeding grounds to ensure that they've accumulated enough reserves for when they're here, and then the timing also needs to be correct that they're giving birth when they're actually here because the conditions are much more favorable for their newborns. So if we zoom into the reproductive cycle of a southern right whale, it can be divided into 3 phases, and together these phases last about 3 years if we're looking at a healthy reproductive cycle. So the first phase is gestation. That lasts for about 16 to 18 months. And this is sort of energetically costly. Obviously, like, it takes a lot of energy to grow a baby whale inside of you. And then when they're at the coast, they give birth, and you then have the lactation phase, which is an incredibly energetically costly phase. Because, as I said, they're not eating at all. They are just making use of their accumulated reserves to then provide milk to their offspring. And then finally, you have the last phase that is not so costly. That's where they go back to the feeding grounds, they're foraging again, and they are recovering from the condition that they lost. They're building that up again. So, due to the high energetic cost of their reproductive cycle, their reproductive success is then very much linked to their foraging success. So right whales feed on Antarctic krill, which is that little shrimpy looking thing over there. And it's really interesting because they're quite small, and you imagine how many of those a whale would have to eat, a 40-ton whale would have to eat to gain all those reserves. So there have been studies like the top one over here that show that reproductive success in right whales is influenced by krill density and climate cycles. So when you have years that climate is increasing the krill production, then you'll have a very successful reproductive year. When krill is low, you'll actually see that reflected in the calving of the right whales. But then quite concerning is we have other studies like this one at the bottom over here that is showing that climate change is influencing krill density and distribution, and that is really having an impact on Southern Ocean predators and the recovery of animals like baleen whales. So that's quite concerning. If we look at the impacts of these krill, the density distribution of krill in relation to climate change, specifically for the South African population, we've noticed between the 1990s and 2010s that they've actually shifted their foraging strategy. They're feeding more north, and they're also feeding on a lot more copepods, which are other little thingies, as opposed to krill. We've also seen between the 1980s and 2020s that our females are about 25% skinnier than they used to be. They've had a decrease in body condition. And then finally, we've also noticed from about 2009 that the calving intervals are increasing. So normally they should be every 3 years they're having a calf, and now we're seeing that they're only having calves every 4 or every 5 years. So a 4-year cycle is linked to an animal taking extra time to recover. So it'll have a calf, and then instead of taking just that little time to build up its reserves again, it needs that extra year before it can start another calving cycle. And then a 5-year interval is linked either to the loss of a near-term fetus, so just before the calf is meant to be born, it spontaneously aborts, or sometimes if they do have a calf but it dies really soon after birth, then we don't consider that a successful reproductive cycle, so that would be a 5-year interval. So all of these studies have really been looking at the impacts of climate change and prey distribution on the adult females, but none of them have really looked at what it means for the calf. So that's why I decided to do my PhD, because calves are obviously the future of our right whale populations, so we need to really understand what is going on. So how does this change in prey availability influence an adult female's ability to raise her calf, so lactation and calf rearing? So to do this, we had to start with some field work. So sample collection was over 3 years, so 3 whole years of my life was dedicated just getting samples of our right whales. And that happened in Hermanus in Walker Bay, so I was just on the other side of here. And we did that in 2022, 23, and 24. So every year for July, August, and September, we'd take 2 weeks where we'd go out and do fieldwork that focused specifically on cow-calf pairs. So the big basis of the study was drone footage. So we'd go out, we see a cow-calf pair, and then we would launch the drone, and we'd spend however long it would take to get a really clear image of the right whale, both the mom and the calf, lying nice at the surface of the water, nice and straight, flat, no obstruction. So sometimes that would take like half an hour before an animal would decide to get in the right position. Or sometimes they would just be very, very difficult, and our battery would die, and we just have to give up on that one. So once we had our drone footage, we'd then bring the drone back, and then it was time for the biopsies. So the biopsies look very intense, and am I allowed to say badass? I feel like a badass when I have the crossbow. But it's really not a big deal at all. So we just have, you can sort of see the dart there that's got a little steel tip. You get quite close to the whale, you shoot it, it pops off, and it takes a teeny tiny little bit of skin and blubber. They hardly ever react. You wait for them to swim away, and then you just reach in, you grab the dart with the sample, and you move on to the next cow-calf pair. So we had the drone footage, which is going to be like the backbone of every chapter of my PhD, and then the biopsy samples that we use for the accompanying analyses. So how did the field work actually go? 2022 was lovely, the sun was shining, and I was happy all the time. 2023, our drone had a very unfortunate incident with a bird, so we couldn't do anything in September, which sucked. And then in 2024, that looks a little bit like the Vol Dam, but actually it's Walker Bay. So for July and August, the water was this horrible, disgusting brown color, and you couldn't see a thing. So we only got samples from September in 2024, which is not great from a science perspective. Anyways, we move. Things don't always go according to plan, but what can you do? So we get to chapter 1, which is the aerial photogrammetry. So the idea behind this is we want a real picture of a whale that kind of looks like this diagram. So you'll see this whale is like lovely and perfectly straight, and it's not bent, nothing, because we wanted to use that picture to get measurements. So ideally, we want a picture like this. So I got to watch hours and hours and hours of video footage waiting for these whales to get perfectly straight. They're not dipping, arching like that. They're not rolling. They're not doing, just perfectly straight with lovely environmental conditions where you can see the whale perfectly clear. So you see the tip of the rostrum, and you also see the notch of the fluke. You can see the outline of the body. It's lovely. There's not like massive splashes. Perfect. But then often you get something like this, where you have a lovely straight whale, except you can't see it. Or you get the opposite, where the environment is stunning, and you sit and watch for hours, and you're swearing at this whale, saying, can you please just straighten out? So in reality, and this is very much the reality of marine data collection, even though I recorded 209 animals, I was only able to use footage from 41 cow-calf pairs. So that's only 81 animals. That's less than a 50% success rate. Nonetheless, we move, we do what we can. So we're back to this image that we have there. So essentially, if you can imagine that perfect picture of the whale, we then put that image into a custom R script, which for the scientists, you'll know R. For the rest of you, it's a torture device that they use for us scientists. But basically what we did then is you can mark points. So on the tip of the rostrum to the notch of the fluke, that'll give you the total length of the animal. Then we also got measurements like from the tip of the rostrum to the eye, which will give you the length of the head. And then also from the tip of the rostrum to the tailstock, which is, well, I don't know, the tailstock you can see. So the reason why we did that is because the way that the blubber is deposited around the shape of the whale, there's not a lot of blubber in the head and in the actual fluke. So we needed to take that account when we get to our later calculations. We also took width measurements at 5% increments of the body. So the whale gets divided into basically like 100% whale, and at every 5% of the length measurement, we get the width measurement. So that was really important because we have a database that has a ratio of height to width. So if the width at that segment is so long, then the height of the whale should be however much. So that all comes from stranding data, and that's why what we do here at Marine Dynamics and Dyer Island, where we do the stranding response, is super, super important, because all of that kind of information comes to the science and it's really useful. So once we had those measurements, they first get measured in pixels, and then you take the details of the drone camera that you used and you do a little conversion, and then you can get those distances in meters. And then from that, I could feed it into this horrifying equation to get a body volume measurement, and then into a slightly less horrifying equation to get a body condition index. So body condition is kind of a standardized measure of how big the whale is, because if we use volume, you're not really taking into account a longer whale will naturally have more volume, even if it is kind of skinny, if that makes sense. Whereas a shorter whale might have more volume because it's really fat, but it's short. So the body condition index kind of standardizes for length. And it's a really simple score. So if you have a positive body condition value, it means that your whale is in a relatively better condition than the rest of the population. And if it's a negative score, it means it's in a relatively worse condition. So to get to a little overview of the results, then we have the calves and then the lactating females. So in the purple, at the top, you've got the calves, and you can see that's the length measurements. So they start pretty small in July, about 5.5 meters on average, and then they grow, and then really between August and September, that's where you see quite a bit of growth. Whereas the females obviously didn't grow because they're adults and they shouldn't be growing. But you do see a bit of variation. So the larger females kind of arrive. So larger females arriving sort of early in the season, and then by September, you have a lot more variation. So those smaller females start to come in. Then in terms of body condition, again, your calves are starting here with a low body condition, mostly negative. But then by the end of the season, you can see that they have overall a positive body condition score. Where the females are doing the opposite, where they start with a positive body condition score, and then it decreases, and by the end of the season, they're in a negative body condition. So those are the actual measurements that we took. I then took the actual measurements and I did some statistical modeling, which again, horrible torture device for scientists, but you can use a model. We take all the measured points, we put it into a statistical model, and this is the decline of female body condition. So it's not a surprise, the females are going to convert their accumulated reserves, they're going to convert that into milk, and their body condition is going to decline. So the rate that we calculated is that they lose about 0.27% of body condition per day. And if you add that all together over the 70-day sampling period that we looked at, it's about 19% of body condition that they lose. So that's completely normal, no surprise, they should be losing condition. But in a South African context, we need to pause and think. So we have this 19% seasonal body condition decline. And then if you add it to that earlier thing that I mentioned, where our whales are about 25% skinnier already, you're looking at like 45% loss of body condition, which is not great. So you have to think, how is that going to influence their ability to recover? And that's why we're seeing those 4 and 5 year calving cycles, because they need to take longer to recover these reserves because they're in such poor condition. Then we move on to the calves. So calf growth in length, you'll see there's 2 plots, because the calf length growth didn't want to do a basic linear model, which if you're a scientist, you know we always hope for a linear model. So I had to use a GAM for that, which basically just shows in the green over there, they steadily increase in length and then it kind of starts to balance out towards the end of the season. But a GAM you can't really use to calculate the daily rate. So we went back to the linear model, which is on the, what is that, right? The blue one. Okay. So from that, we calculated that calves are growing at about 2.7 centimeters per day, and that means they increase over that 70-day sampling period about 1.9 meters. For volume, lovely linear model, so steady gain of about 0.066 meters cubed. So over the 70-day period, they're gaining about 5.5 meters cubed in volume. And for body condition gain, they're gaining about 0.12% per day, which equates to 8.2% over the 70-day period. So those are just numbers to you and to me. So I had to go look a little bit, read a bit, see what that means. If we compare it to the Australian population, which is sort of considered quite a healthy population, that's where it became interesting. So the females are losing body condition at approximately an equal rate in Australia and in South Africa. But our calves are growing significantly slower. So in Australia, they're growing at about 3.2 centimeters per day, where in South Africa, only 2.7 centimeters per day. And they're gaining condition in Australia at a rate of 0.081 meters cubed, and here only 0.66 meters cubed. So that's a little bit worrying. So there's 2 hypotheses that we proposed for why that might be. The first is that there might be a lower energy conversion rate between the mom and the calf. So the mom might be giving however much energy, but the calf is not taking that up and not using it to grow as fast as the Australian population. The second thing that we hypothesized might be related to the female. So it could just be that the energy demand outside of lactation here on the South African calving grounds is more. So that could be related to rougher seas or more disturbance, maybe more social interaction, but they might be spending more energy on other things. So that's why we see it in the loss of condition, but it's not necessarily translating into the calf growth. So that was the aerial photogrammetry. We now move on to chapter 2, which is endocrinology. So that is just hormones. So this is where the biopsy samples came in. So yeah, there's me and my crossbow again. I do love that photo. And then if you look over there, so that's when we unscrew the tip. So the tip has got a little barb in it, which keeps the biopsy sample in that tip. And then you sit and you try and get it out of that tip. And sometimes it's really easy until there's a camera somewhere, some film crew wants to film you, and then you sit there and you start blushing and it's taking you half an hour and the stupid thing won't come out the tip. But anyways, when you do get it out, it looks like this picture at the bottom. So you can really see how small it is in relation to a 40-ton whale. It's a tiny, tiny piece of, hold a lot of power. So for the endocrine chapter, we use the blubber, that white part, And then the skin we save for later, for chapter 3. So unfortunately, sometimes you shoot and you get the wrong angle and then your biopsy doesn't have any blubber. So you get this long piece of skin, you can't really see, sorry, my top was black. It looks like skin spaghetti and it's like this long and it's quite useless for hormones. So not great, but we don't want to shoot the whale twice unnecessarily. So that's another place where we can lose the sample size because we take the shot, you're unlucky, you only get skin, there goes your sample size. So the reason why we need blubber for hormones is because hormones are fat soluble. So there's 2 hormones that I was looking at. The one is T3, so it's triiodothyronine, and that's because there's 3 iodine attached to there, 1, 2, 3. So that is one of the thyroid hormones that you have. So you have T3 and T4. Susanne is showing me I must speak louder. So T3 and T4, T3 is the more active one. And that hormone is very important for regulation of metabolism in all animals. And then we have on the, again, left and right, left, we have cortisol, which falls under the class of glucocorticoids, and those are stress hormones. So stress is quite a complex thing, and it's not necessarily what we know as the common definition of stress, like I am currently very stressed. But stress does things like it also increases your metabolism and increases your fat mobilization. So that's really important in the context of lactation, what we're looking at. So I produced these lovely box plots that are very boring to most of you. I'm sure they were quite boring to me as well, because even though it looks like there's some kind of difference, the result was that there's no statistical difference between the hormone concentrations of females in good body condition, which we got from the drone data, versus those in poor body condition. So that was quite upsetting to me, but then luckily I could do even more statistics, which showed me that the problem was not in the pattern, the problem was in my sample size. So you get this lovely thing called a power and a sensitivity analysis that tells you if you want to see any detectable patterns, you're going to need at least so many samples. So this power analysis told me that I need about 100 animals per group, so 100 in good body condition and 100 in bad body condition. So as you remember with the drone footage, you don't always get good drone footage. Now you need drone footage and you need a biopsy with blubber. So your sample size goes crash bang down. So that's really a challenge that we have, but it just means more opportunity to go on the boat. So we need to continue this long-term monitoring so that we can really see these patterns. But what we did see is that there's a seasonal hormonal regulation of lactation. So you have, on this side, your glucocorticoid, so that's cortisol, stress hormone, and then on that side, you have the T3. So what happens with both of them is that at the end of the season, they really decrease. And basically what that is showing is that when it gets to the end of the season, the females are like, you know what, I'm out. I'm done mobilizing my own reserves for you, for my calf. Calming that down, you got to start being on your own. And that makes a lot of sense because a right whale is what we call a K-selected species. And that means that your animals, so like humans, are K-selected. So that is a term that we use for animals that are quite long-lived and that have usually a single offspring at a time or very few offspring at a time. But they have multiple reproductive events over their lifetime, so it's not just one batch of offspring and then they die. And their parental care is very high. But what that means is that they are going to prioritize their lifetime reproductive success over this individual event. So in order for them to prioritize lifetime reproductive success, they need to have a long lifetime. So they're going to prioritize their own survival above that of their current calf so that hopefully in future they can have another successful reproductive event. So that complete downregulation of hormones where they're not mobilizing as much fat to the milk, they're decreasing their metabolism, that is because they're holding onto their reserves to ensure that they have enough to then migrate back to their foraging grounds so that they can repeat the reproductive cycle again. So it's a very careful balance between providing for my calf, but also prioritizing my own survival. So is that concerning that they're doing that? Maybe not, but we do see that they've changed their foraging strategy. As I said earlier, We do see that there's a decrease in body condition. So the potential for a trade-off really is there, where they're going to say, sorry, calf, I'm out. And they're going to really prioritize themselves. So time will tell. We'll have to see more long-term monitoring what that's going to mean for the population in future. Then we get to the last chapter, which is stable isotope analysis. So we're back on the biopsies. This time we're using the skin. So stable isotopes, very cool. You use like a tiny, like if you go like that tiny little hole, that's how big of a size sample you need. It's amazing. It's also quite an inexpensive analysis, so it's really great for research where funds are often quite limited. Yeah, so I think very few of you maybe know what stable isotope analysis is. I have vivid memories of me crying in science class in high school at isotopes. They were horrible. Now I love them. I think they're super, super interesting. Basically what an isotope is within an element, you get different variations where you will have the same number of protons, but you'll have different number of neutrons. And then depending on how many neutrons you have, it might be a stable isotope, which stays, it's stable, or you could get a radioisotope, which degrades much quicker. So we're looking at the stable isotopes, specifically of carbon. So carbon is often used to infer location of feeding, especially in the ocean, because you have what you call an isoscape. So it's like the landscape of isotopes within the ocean, and when you look at the carbon isotope signature, you can see where this animal was feeding. But I didn't do that. I did something completely different. So because the calves are not actually feeding on anything else other than the milk that they get from the mother, and the mother is not feeding while she's feeding her calf, you get to see the isotopic signature of where the mom was feeding. And then when you take the isotopic signature of the calf and you subtract the mom, you get to know what's happening with the milk. So if none of that made sense, all you have to know is if you take the isotope value of the calf and you subtract that of the mother, if you get a negative value, it means that the milk has a high lipid content, which is great because calves need very high lipids to sustain their rapid growth that we saw from chapter 1. If you get a positive offset, so you take calf minus cow and that value is positive, it means that there is a low lipid content, so it's not great for calf growth. So now the box plots, and what we see there is that the females in good condition from the drone photogrammetry, their offset is overall negative, which is good. So that shows that they're producing high lipid quality milk. Whereas the females that were in poor condition, the offset between them and their calves is positive. So that's bad, sad face, because there's a low lipid content in their milk. So that again just shows that they are very typical of a K-selected species where the females are prioritizing their own survival above prioritizing the calf because they are prioritizing lifetime reproductive success. Cool, yeah. Okay, so as you can see, we've seen lots of little pictures, a little bit here, a little bit there, and they've often been limited by things that are uncontrollable, so like poor weather conditions, no blubber biopsies, that leads to low sample sizes, and then we get incomplete pictures. But when you put this all together, you get a lovely little puzzle piece, and that's why I very, very strongly believe in multidisciplinary research. So we need to be looking at the same situation from different aspects so that we can get a bigger picture, especially in marine research where we have so many challenges because, let's face it, we are at a disadvantage being terrestrial beings trying to research marine creatures. So at the end of the day, we are saying that climate change is impacting their prey availability, that's impacting their ability to raise their calves. So what do? Do we just stop climate change? Easy solution. Obviously not, that's quite difficult. But there are things that we can do. So this kind of research feeds into management and policy where we can do things like manage shipping lanes, we can try and reduce noise pollution, we can try disturb the whales as little as possible. So anything that's going to unnecessarily increase their energy expenditure, we want to try and minimize that as much as possible. Because our whales are in such poor condition, they really need all of their energy and reserves to be able to feed that into their calves. The other thing that's super important is collaboration among researchers. So we don't just want population-specific estimates, we obviously do, but we want to ensure that each right whale population, the same kind of research is being done with the same methodology so that we have comparable research, and then we can get global assessments. So for that, we have the Southern Right Whale Consortium, which is a really, really cool collaborative thing. We have meetings every now and then to just discuss what we're doing, what the results are, how we can improve our research, how we can standardize, and in that way we just, again, we get to see a much bigger picture. So yeah, that is it from me. Thank you so much for listening, and if you have any questions, please do ask.
Are humans exploiting the krill fields?
Okay, so we do have krill fisheries. That is not the main concern in the sense of right whales. The main concern is climate change. Obviously, we do want to manage the krill fisheries as much as we can, but it is not the main concern for the changes in krill distribution and availability for right whales.
Okay, another question? Yes.
Surely the Australian whales are affected by climate change equally as we are, and why are their whales appearing to be in better condition than ours?
Okay, so that's a very good question. So the Australian population, they are healthier than the South African population, and there's a paper's just come out now that's showing that they are actually also showing signs of being affected by climate change. But each population has different foraging grounds. So one foraging ground might be affected more than another, and then that's going to reflect in the right whale population.
Thank you. How many years is required to maintain the population growth of this just 5-year period between births? Is the population growing, falling back?
Okay.
What is required?
I think I understand your question. So at the moment, the maximum biologically possible rate for population growth is about 7%. Our population is still growing, but it's growing slower than it used to. So it was at 7% and it's now declined to about 6.5%. So it is growing, but growing slower. Does that answer your question?
Yeah.
Okay.
Yes.
Hi, Loraine. I know climate change is a huge topic. You say that the numbers are decreasing within the mom's fat and the young ones, the mother does not take care of the young one. So with temperature rising and sea level rising, what exactly about climate change that is making a huge variation from the 90s until the 2010s? Thank you.
Okay, so krill, the Antarctic krill that the right whales are feeding on, they are very dependent on sea ice because they use that as a nursery and a breeding ground and habitat for their young. So with global warming and climate change, that ice is melting and it's creating less habitat for krill. So if they have less habitat, there's less krill available, and then there's less krill for the whales to feed on.
Okay, but that's interesting. So back to your question, so that's why we're thinking it's the krill trawlers automatically, that the krill's being taken out, but krill is still a massive problem, yeah?
Well, climate change is still a massive problem, yes,
The krill?
Yes.
Okay. Yeah.
We've heard a lot about the climate changes, but can you just expand a little bit more on the effect of the slowing down of AMOC and possibly the southern circumpolar currents?
I must be honest, that is not my field of expertise at all. I'd be happy to share. I do know someone who's very, very knowledgeable on that, so I can share his details with you. That is not
in terms of krill production.
Again, not my field of expertise at all. So I can tell you that different regions are experiencing different effects, but that's as far as my knowledge goes. Thanks.
That's like Tom, he's our resident geologist. You want to know. Yes.
want to try and ask the scientific question. The question is, if you have to put a percentage to the reduction of crow because of climate change and the reduction of crow because of fishing, and what percentage would that be? In other words, would it be 90% climate change or 10% fishing? Or what is that more or less?
These are such interesting questions. It is a very vast field and I'm not an expert again. So I can say to you that climate change is substantially more than fishing, but I can't confidently give you percentages, unfortunately.
Can we do a round of applause? Thank you so much, Loraine. It's really amazing. We've got some incredible questions, and I'm sure we'll get more answers as we go along. Lorraine's definitely going to work on a lot of research projects, and we will be excited to share it with you. Watch this space. So thank you very much, everybody, for being here for our first Friday evening. Are we seeing some people again on Thursday morning for the Birkenate? Let's go and say, Birkenate, Patricia's not here tonight. Glenda, do you know it's fully booked? Because I know Patricia, it is fully booked. Okay, but for those of you that we'll be seeing on Thursday, otherwise the rest of you for another marine evening. And I would like you to enjoy some lovely soup and bread made by the Great White House.